Hey guys, I wanted to do a couple extra examples of our instantaneous and average rates of change. So I picked three problems for us to look at, and then hopefully these will help you get through the three homework problems that you had in class. So in the first example here, we have a table similar to our heart rate problem that we had done. And the table is showing the distance-time relationship for a 1994 Ford Mustang Cobra accelerating from a standstill. So we can see the elapsed time in seconds. They have different times from 12 all the way up to 20 seconds, and then the different distances at each of those times that the Mustang had moved forward. So as we're looking through the part A, it says point P is the point 18, 545. And we can see that's right on our data table right there. And we want to find the slopes of the secant lines PQ when Q is the point on the graph with time 12, 14, 16, and 20. So what they're really asking us to do is just find four slopes of lines where we're using one point as 18, 545 every time. And then our other point is coming from each of those time frames. So if we're looking at the first time they gave us when the time was 12, they wanted us to find at the point 12, we knew the point was 12, 240. Because at 12 seconds, the distance was 240 meters. They want us to partner up that time with that given point that they gave us, P, which was that 18, 545 point. So we're just going to find the slope using our slope formula with those 2 points. So again, we're just going to go y2 minus y1, so 545 minus 240, and then x2 minus x1, 18 minus 12. I went ahead, did the calculator work, and found out that that was about 50.833 meters per second. So what they really want us to do now is keep calculating slopes, but changing our initial point each time by grabbing the new time. So the next time they gave us was 14. So now they want me to partner up this time of 14 with that time of 18. So again, I just want to find that slope for that new line that they're creating. So I'm going to do y2 minus y1, x2 minus x1. And again, I went ahead and calculated that out, and I got 41.25 meters per second. And then they just kept repeating that, picking a new time every time, but we're always partnering up that new time with that original point at 18. So when the time was 16, now I'm going to find the slope between these 2 points. And when I went ahead and calculated that, I got 52.5 meters per second. And then lastly, they did the time was 20. So now we went past that and we're going this way. So we're going to use those 2 points. And again, I went ahead and calculated that already to get 52.5 meters per second. So for part A, when they asked me to find the slopes of all those secant lines, I was just finding the slope between the two data points at the given time, always at 18, 545, and then grabbing the second point from each of the times they asked me to find. Part B then wants me to estimate the slope of the tangent line at P by averaging the slopes of two secant lines. So remember, my point that they wanted me to look at for P was this 18. So out of all of the secant lines we really looked at, we want to grab the two that were closest to that point there. So the two closest ones I had were the ones before it and the one right after it. So if I'm going to average two, I'm going to average the left side average rate of change and the right side average rate of change. Now in this problem, it just worked out that they had the same exact rate of change. When I was to the left at 16 and when I was to the right at 20, I got the same thing. But if they were different numbers, remember, you would just take your two values and average them by adding them up and dividing by 2. And that would get me my approximation for my slope of my tangent line in that problem there at that point P, so at 18. That's really all we had to do in that example there. Similar to what we did with our heart rate problem, except they change the wording a little bit to kind of really make that connection between the average rate of change, which is what we found on each of those intervals, and how they define the intervals for you. All right. Example 2 moves on to a curve where we have a function, and it's again worded the same way as the last problem, but instead of being able to take our data from a table, they gave us a function. So we can kind of make it and treat it similar to a function, to a data table by just using the function rule to write points. So for all of my slopes on my secant lines, point P is always this 0.39. And it's lying on this curve y equals x squared. So any other point I get, the x and y coordinates are going to be found using this rule right here. So when they tell me Q is the point x comma x squared, what they're really just telling you is that you're going to pick some value for x, and then we're plugging it into that function, which is defined as x squared. So in this case right here, when they want me to look at the point 2.99, that's my x coordinate for my point. Kind of like how we went to our table up there and found our x coordinates at 12, 14, 16, 18, and 20. But instead of being able to get the y coordinate straight from the table, we're just going to use our calculator. So to find the y coordinate, I'm just going to square that because that's what the rule wants me to do for this guy. So I went ahead and I squared 2.99 and I got 8.9401. Once I have that, then I can go ahead and take this data point that I now have with the original point that they gave me. And there's my P and there's my Q. And those are the 2 points we want to use to find the slope of our secant line. So I'm just going to go ahead now and use good old slope formula. So again, just like we did in all the problems up above, I'm going to do y2 minus y1. And then x2 minus x1. All right, again, I went ahead on my calculator. I did that math out to get my answer. And I found out it was about 5.99. And I don't have any units for this guy. We don't know what that function represents. All right, so I really did the same thing for the remaining 2 values there. So again, all I'm doing is taking the coordinates that they gave me. Those are my x values, plugging them into the function so I can get the y value, and creating an ordered pair. So I got 3.01, I went to the function, I squared it, I got 9.0601. I went 3.001, I squared that to get my y coordinate over here. I got 9.006001. That's fun. All right, and then I'm not going to write out my slope formulas, but after I have these points, I went ahead and I used my slope formula. So I took each of these as y2, going back to this 0.39 as my y1, x2 minus x1. So I just found the slope between the 0.39 and each of these 2 points here. And when I worked it out for this guy, I got the slope to be 6.01. And when I did this one, I got the slope to be 6.001. All right, you can do the work on that out if you really, really want to, but I think we all know how to find slope now. Once we had these parts completed, then what we want to do is, it says use your results from part A to approximate the slope of the tangent line at P. So remember, what we're doing in each of those points there, you can see is that as we're getting closer and closer to 3, so either when I went to 2.99 up to 3, or from 3.001 to 3.001, I can see all of these points are fairly close to 6. So if I'm going to approximate the slope of my tangent line, since all of these values were pretty darn close to 6, I'm going to say the slope of my tangent line was about 6. And then I can go ahead now and write my equation of my tangent line, because again, to write an equation of a tangent line, we need a slope, which we found in part B, and we need a point. They're telling me to use point P, which they told me in the directions was 3.9. So if I put those together, I can write the equation of a line. And again, I love my point slope formula. So I'm just going to go y minus 9 equals 6, that's my slope, parentheses x minus 3. And I can leave my answer in point slope form, but I know a lot of you love slope intercept. So all we have to do to get this to slope intercept is distribute and then add that 9 over. And if you feel better about that point slope form, go ahead and use that answer. All right, so those first two examples that we have here are really just using slope of secant line, using 2 points, either 2 data points from a table or using data points where you had to find the y-coordinate by plugging into a function. The last example I want to look at is similar to the last example we did in class, where we went a little bit crazy with the algebra, and we used the definition for average velocity. And remember, we defined average velocity using that function f of a plus h minus f of a all over h. That was that fun formula that we had done in class when we talked about average velocity. And what's changing in this problem right here is that we want to find the average velocity, but instead of finding points and using slope formula, we're going to create a model for our average velocity so that if I were to ask you to do 10 of them, I wouldn't have to do 10 slope formulas. I could write one model and then just plug in my gap value. When they're giving you these values right here, that 0.1 and that 0.01, remember those are our gap. That's how close we're trying to make those points get together. So those represent the h function, our h value in our function. And then a is the point we're trying to find the velocity at. Think of your, find the velocity at this time. So for this problem, a is 4. So what we're going to do is, instead of saying our average velocity is f of a plus h, we're actually going to use f of 4 plus h because our a is 4 for both of those problems. So let's just do the math in that. So I'm going to do my work up here a little bit. So I have f of 4 plus h, which means I'm going to go into my function, and I'm going to replace that t right there with 4 plus h. So I'm going to get 100 minus 4.9 times the quantity of 4 plus h squared. I'm going to go ahead and multiply that out. So I'm going to get 100 minus 4.9 times 16 plus 8h plus h squared. I'm going to distribute that. I'm going to get 100 minus 4.9 times 16, which was 78.4, minus 4.9 times h, which was negative 39.2h, and then minus 4.9 times that guy. All right, and then I can actually clean this up one step more because I have 100 minus that 78.4. So I can actually do that math, and I'm going to get 21.6 minus 39.2h minus 4.9h squared. So that's my formula for f of 4 plus h. So that's what I'm going to end up putting over here in this part of my function. Now f of a, again, a is just 4, so I'm going to go into my function and replace 4. I'm going to do that right here. So 100 minus 4.9 times 4 squared. Went ahead and did that on my calculator, and I found out that was 21.6. All right, so what I'm going to do now is take all of this here and all of this there and build my average velocity formula. So my average velocity is f of 4 plus h, all of this stuff, minus f of 4, which is 21.6, all over h. The 21.6's will cancel. So I'm left with negative 39.2h minus 4.9h squared all over h. Both of these have an h, so we're going to cancel one of those out. So we're going to get negative 39.2 minus 4.9h as long as h does not equal 0. So by doing all of this work now, I have a rule that's going to tell me my average velocity is equal to these values right here, negative 39.2 minus 4.9 times h, where h is the gap. That's how close together my points are going to be. It's the distance in time that we're looking at here. So for this problem, h was 0.01. So my average velocity is just going to be negative 39.2 minus 4.9 times 0.1. And I went ahead and found out that was negative 39.69 meters per second. And then using the same formula again, my average velocity is negative 39.2 minus 4.9 times 0.01. And I got that to be negative 39.249 meters per second. As we're looking at these rates of change, we can see that as we make that gap get smaller, these values are changing slightly. And what's going to happen is as we go from average velocity to instantaneous, we want these gaps to be as close to zero as possible. So if I now want to find my instantaneous velocity when t is 4, I want to let h get pretty darn close to zero. So if I'm looking at that model and I let h get close to zero, then that negative 4.9 is going to eventually go away. So my instantaneous velocity when t is 4 seconds is just going to be negative 39.2 meters per second. All right, so hopefully that helps you get through the 3 problems you had for homework. If you still have any questions, please reach out to me and let me know.